Now we're going to look at some applications of linear equations and systems of linear equations. And one of those applications will be curve fitting. So in example 1, we want to determine the polynomial whose graph passes through these points. Now, if we were to graph these points, notice that we're forming a quadratic here. You have to have 3 points to form a quadratic. You would have to have 2 to form a linear equation. And we talked about how to do that back in 171. We would find the slope and then find the y-intercept, and then we could write it slope-intercept form. So for a linear equation, you got to have 2 points. For a quadratic, you got to have 3. For a cubic, you would have to have 4, and so on and so forth. So in this case, we have 3 points. They're well defined. Notice they're not in any straight line. There's definitely, if we were to graph this, and our picture does graph that, there's definitely a quadratic function that would model that behavior with those 3 points. So our polynomial generically could be written this way. So our goal is to take those points, substitute it into our generic equation for a polynomial of degree 2, quadratic, and then figure out what those coefficients will be. So let's do that. So we have points 1, 4, 2, 0, and 3, 12. So notice each point has an x value and it has a y value. We're going to substitute that x and y into this model. And then our goal is to figure out what a sub 0, or I call that a naught, is a1 and a2. So let's substitute in. Our y value is 4 in this case. And our x is 1. So our equation is 4 equals a sub 0, or a naught, plus a1 plus a2. The second point is 2, 0, so our x-coordinate is 2 and our y is 0. And we're just going to substitute that in to the y and all the x's in here, just like we did with the previous one. So our equation, if we were to simplify this just a little bit, we get that. And then our last one, substituting in the x and the y again. 12 is equal to a naught plus a1 times 3 plus a2 times 3 squared. So our equation is 12 equals a naught plus 3a1 plus 9a2. So notice in this case we have 3 equations and we also have 3 unknowns. So if we want any possible chance of finding a specific value for those unknowns, you have to have as many equations as unknowns. If you have less equations than unknowns, then that means we have an underdefined system, and underdefined systems typically will result in infinite solutions. Now, if we have more equations than unknowns, then we have something that's called an overdefined system, which means we may have anything could happen, really. I mean, you could end up with one solution where one of those is a linear combination of the other one. So you could end up with one solution, no solutions, because something may be contradictory, or we may have an infinite number of solutions. Just depends on the system. But this one's defined just right. We have 3 unknowns. We have 3 equations. So now that we have those equations, I'm going to rewrite them on the next page so that we can see your system here. So we have 4 is equal to a naught plus a1 plus a2. That resulted from that first point we substituted in. 0 is equal to a naught plus 2a1 plus 4a2. That came from that second point. And the last point gave us this last equation, 12 equals a naught plus 3a1 plus 9a2. So let's solve this system. Now remember, when we write everything as an augmented matrix, we really need to think about these with the variables on the left. So we really need to rewrite these equations. And you don't have to formally rewrite this as long as you know how it will line up in the matrix. But just to kind of give you an idea of what it would look like. So this is the way it really should be written. Now remember, that first column is going to represent those coefficients of A0. Second column is going to represent the coefficients of A1. And the third column will represent coefficients of A2. And then there's our equal sign. And then the numbers on the right-hand side. Now, I know we could pop this into the calculator and do RREF, but remember, that's not the point of this class. The point is to be able to understand what the calculator's doing. So we're going to do some Gaussian elimination. Now, we already have a 1 in the top left-hand corner in that A1 slot, so we're good there. Now we want to eliminate this guy and this guy. And we're going to use those elementary row operations to do that. So we're going to take row 2. And we're going to replace it with row 2 plus -1 times row 1. We're going to take row 3 and replace it with row 3 plus -1 times row 1. So notice in both of these cases, to eliminate this term and this term, I'm using row 1 to help me do that. So let's perform those operations. That top row is going to remain the same. When we perform it, the operation on the second row, we're going to take row 2 and add -1 times row 1. So 1 plus -1 times 1 is a 0. So we zeroed out that item. 2 plus -1 times 1 is 1. 4 plus -1 times 1 is 3. 0 plus -1 times 4 is a -4. So now our operation on row 3, we're going to have 1 plus -1 times 1, which will be 0. So we've zeroed out the A2 in one slot and the A3 in one slot. So we're on our way to our REF. So let's finish this row. So we're going to have 3 plus -1 times 2, which is 1. 9 plus let's do that again. It's going to be 3 plus -1 times row 1, which is a 1 there, which is going to give us a 2. Then we're going to have row 3, so now we're at the 9, plus -1 times 1, which is 8. And then 12 plus -1 times 4, which is also an 8. So far so good. Now we want to zero out this entry in the A32 slot, third row, second column. So we're going to take row 3 and we're going to replace it with row 3 plus -2 times row 2. So notice I'm using row 2 here instead of row 1. If we were to use row 1 to try to zero out this term, then we would end up undoing what we've done here. So you always want to use the row directly above to try to eliminate terms and to get zeros in those key slots. And this guy's going to definitely be a key slot. So notice the first two rows are going to stay the same. So then we're going to have 0 plus -2 times 0, which is still going to be a 0 here. Then we're going to have 2 plus -2 times 1, which is 0. And then we're going to have 8 plus -2 times 3, which is a 2. And then 8 plus -2 times -4, which is a 16. So now we're on that bottom row. We really need a 1 right here. That's the first non-zero entry. So to get a 1 there, we're going to replace row 3 with 1/2 times row 3. First two rows stay the same. That third row is going to be 0, 0, 1, 8. So as of right now, we already know what A2 is going to be, which is great. But now let's take that step further and let's get this in RREF form. This is already in REF. So to go and do that backward phase for Gauss-Jordan elimination, we need to eliminate this entry and this entry. And we're going to want to use that third row to do that, just so we don't undo those zeros and those ones and those key slots in the first and second row. So row 1 will be row 1 plus -1 times row 3. And if we do that, we'll get a 0 in the A13 first row, third column slot. Row 2 we can replace with row 2 plus -3 times row 3. So notice that in this backward phase where we're trying to zero out those items above, we are using that bottom row to help us do that. And that's key because of those zeros. It really won't change anything in those columns. So if we do that, let's look at row 1. So row 1 is row 1 plus -1 times row 3. So 1 plus -1 times 0 is still a 1. 1 plus -1 times 0 is still a 1. 1 plus -1 times 1 is a 0. 4 plus -1 times 8 is a -4. And then row 2, we're going to have 0 plus -3 times 0, which is still a 0. 1 plus -3 times 0 is still a 0. 3 plus -3 times 1, which is 0. Be careful, this guy's still a 1. 1 plus -3 times 0 is still a 1. And then I'm moving on to this entry. -4 plus -3 times 8. It's a -28. And then bottom row stayed the same. So using that third row to eliminate those two slots keeps that core set. And by core set, I'm talking about these guys, because we worked really hard to get that 0 there. It keeps that little block intact. I'm going to clean this up a little bit. So let's do that last step. Our goal now is to get a 0 right here. And we can take row 1 and replace it with row 1 plus -1 times row 2. So we're going to have a 1, 0, 0 there. And then row 1 plus -1 times row 2 is going to give us a 24 there. So there's our RREF matrix, reduced row echelon form. So this tells us that A0 is equal to 24, A1 is equal to -28, and A2 is equal to 8. So remember, our format for this was y equals A0 plus A1x plus A2x squared. So if we make our substitutions, the quadratic model here will look like this. Y equals 24 minus 28x plus 8x squared. So there's our final answer for this. So that's the quadratic that will model these particular 3 points. Now we could do all this in the calculator. Just to kind of remind you, the calculator is a great way to double check your work on a test, quiz, or final exam. But remember, that's not the point of this class. The point is to understand what the calculator is doing so that we can use a program later, or we could program something powerful like MATLAB, which a lot of engineering companies use. So it's important to understand there's row operations. So if we wanted to double check this answer, we're going to go to second matrix, go over to edit, and this was a 3x4 matrix. And I'm going to type in that original matrix. So after you type everything in, and I'm just going to double check to make sure I've typed everything in correctly. I'm going to go back to the home screen, hit second mode, and then we're going to go second matrix, go to math, and we're going to choose RREF. And then go back to second matrix, and then matrix A. And you'll see that the matrix RREF is going to give us the same thing as we had over there on the other page. So this is a great way to double check your work under the row numbers. This will not work with complex numbers or under anything fun like modular arithmetic. But for now, it's a good way to double check. So let's do one more. Let's look at example 2. In example 2, we want to find a polynomial that's going to fit these points. We have 1, 2, 3, 4, 5 points. So remember what we talked about before. 2 points equals a linear function. 3 will be a quadratic. So if we have 4 points, we're going to have a cubic, or possibly a cubic. 5 points would give us a quartic. So we're talking about a 4th degree polynomial, possibly. We won't know until we start setting things up, because it could turn out that one of those terms has a coefficient of 0. So our model that we're going to use is this a0 plus a1x plus a2x squared plus a3x cubed plus a4x to the 4th. So let's make our substitutions. We have the point negative 2, 3. If we substitute that in, our y-coordinate is 3. I'm going to clean this up. So we have 3 is equal to a0 minus 2a1 plus 4a2 minus 8a3 plus 16a4. Our next point, 5 is the y, negative 1 is the x. Clean it up. Next point, 0, 1. Substitute and so we have A0 plus A1 times 0 plus A2 times 0 squared plus A3 times 0 cubed plus A4 times 0 to the 4th. So this is just 1 is equal to A0. Then we have the point 1, 4. 4 is the y. 1 is the x. And then our last point is 210. So notice we have 1, 2, 3, 4, 5 variables. That means we have to have 5 equations in order to come up with a solution. And we do. We have 1, 2, 3, 4, 5 equations. So our system, and I'm going to write this with the variables on the left and numbers on the right. So there's our system. So this guy's pretty big. There's a couple of ways to approach it. We could simplify this a little bit. We already know A0 is equal to 1, so we could substitute A0 in, and then we would have 4 equations and 4 variables. That's one option. Or, since this one's so big, I'm apt to actually use the calculator to solve this one. And that's fine on the bigger systems. What I want you to understand is how to do this on the smaller systems. I would never give you something with 5 variables, 5 unknowns to do Gaussian elimination by hand. But it's a great thing to do if you get bored one night. So, we're going to go back to the calculator. Second matrix, edit. Now, we had 5 rows and we had 6 columns, so this is a 5 by 6. We're going to type everything in. That third row just had A0 is equal to 1. So we're going to have a 0 for the A2 column, 0 for the A3 column, 0 for the A4 column, and then 0 for everything, and then a 1 here. So I want to double check to make sure I type that in. So I'm going to hit second matrix, and under names, I'm going to choose my A matrix, which was my 5x6. So this pulls it up on the home screen so I can double check everything quickly. So I had 1s down the A0 column, -2, -1, 0, 1, 2 down the A1 column, 4, 1, 0, 1, 4. So this is a typo, so we need to change that. Down the A3 column, sorry, A2 column. A3 column, we need to fix that too. So we need to check our last few columns. This is a great thing to do before you find that final answer. So let's check those. So we have 1, 1, 1, 1, 1, and then 4. 1, 2, 4, 8, 16, and 10. Just double checking again, make sure everything's correct. So now we're going to hit second mode to go back to the home screen. Second matrix, math. We want to do RREF on matrix A. Hit enter. Now, notice the decimals here. We're always going to want fractions. So to turn this into fractions, we can just hit math, hit enter, and that option, that first option, will turn everything into fractions. Even if it's a matrix, it will turn everything into a fraction. So then now we've got this 1. Notice we've got 1s down that diagonal there, and then 0s everywhere else. So this entry right here, that's a 5x5 size with the answers in that last column. That 5x5, we have all 0s except that big diagonal. That's actually called the identity matrix. And we'll talk more about that in the next chapter. So our solution here for this, when we did RREF, gave us the identity matrix for a 5x5. And then it gave us all of our fractions. So A naught was 1. A1 was -5/4. A2 was 101 over 24, A3 was 3/4, and A4 was -17 over 24. So this one's not as nice as the last one. We didn't end up with some fractions, which is perfectly fine. So then our final answer, remember the format that we were trying to fit? We were trying to fit this format. So our polynomial is going to be A naught, which is 1, minus 5/4 x plus 101 over 24 x squared plus 3 over 4 x cubed minus 17 over 24 x to the 4th. So there's our polynomial that fits this model. So how cool is that?